VBB only. Okay, now coming to the working. So you can see that from the equivalent circuit, the resistance, the total resistance between B1 and B2, I can write it as RBB, which is equal to RB1 plus RB2. So you can see these two are in series, right? So the total resistance will be in series, RBB equal to RB1 plus RB2. That is what is given here. When the emitter is open, so I am not giving any input to emitter. When the emitter is open, I am not going to give any input to emitter. The voltage across VBB is applied between the two bases, and the voltage gradient is established across the n-type bar. So you are going to apply voltages, two voltage I am going to apply. One is VBB and one is VE. Okay, our VBB will be always applied, and VE will be applied depending on how you want to operate your device. So when I am not applying any emitter voltage, okay, when I am not applying any emitter voltage, when I am applying only the VBB, so you see it is just looking like a resistance, right? So this VBB will split across RB2 and RB1. So the total voltage VBB will be splitting across RB2 and RB1. So I can say a voltage gradient is established between B2 and B1. So you have an electric field setup between B2 and B1. And that voltage across RB1 is given by V1. So you know it is an voltage division technique. So I can find the voltage across RB1, V1 equal to total voltage into that resistance by this resistance plus opposite resistance. So I can write V1 equal to VBB into RB1 by RB1 plus RB2. So see here. So RB1 by RB1 plus RB2, it is a constant. So I'm going to denote it by a term eta, and eta is called as intrinsic standoff ratio. See, if I apply voltage division technique, I will be getting V1 equal to VBB, the total applied voltage, into that resistance RB1 divided by RB1 plus RB2. And RB1 plus RB2, I am writing it as RBB. It is the series combination of RB1 plus RB2. So this RB1 by RBB is a constant. I'm going to denote it by a special symbol called eta. So that eta is called as intrinsic standoff ratio. So if I simplify, I'll be getting V1 equal to eta into VBB. So I'll be getting V1 equal to eta into VBB. That is what is given here. Okay. And eta is a fraction, right? So eta value will vary between 0 to 1. So typical value of eta will range from 0.56 to 0.75 as given in the slide. Okay, so the total voltage available across the base 1 terminal V1 is given by eta into VBB. What is eta? Eta is called as intrinsic standoff ratio. Intrinsic standoff ratio, and the value for eta is 0.56 to 0.75. Okay, so I'm going to have a voltage now. So this voltage V1 will reverse bias your diode. Why it will reverse bias my diode? Because emitter side I'm going to have 0 volts, and I'm going to have in the emitter side, this side of the emitter you see I'm going to have 0 volt. This side I'm going to have a positive volt. So it is going to reverse bias my diode. So when a reverse biased PN junction diode will not conduct, so the emitter's current is cut off, or I can say no current will flow through the diode ideally, but a very small leakage current because of minority carriers will flow from B2 to emitter. Okay, so this is the first operating principle we are going to study. When I am not going to apply any emitter voltage, the emitter terminal is open. So one end of the diode is going to be open. See here, this side of VE is going to be open. So it is going to have 0 volt. Okay, it is going to have 0 volt. And this side, because I'm applying a voltage VBB, I have some voltage across RB1. So this is going to be some positive voltage. So this side is going to be positive. See, the diode is forward bias only when this voltage should be high and this voltage should be less. But the reverse is happening, you see. So the diode is reverse bias. Reverse bias PN junction diode is going to be cut off, and ideally 0 current is going to flow. But because of minority carriers, some leakage current will flow from B2 towards the emitter. So some leakage current will flow from B2 towards the emitter because of minority carriers. Okay, so that is operation of the device when I'm going to apply zero emitter voltage, or when the emitter is going to be completely open. So now I'm going to apply a positive voltage to the emitter. So I'm going to apply positive voltage to the emitter, and how much ever positive voltage I apply to the emitter, the diode will not conduct unless your VE is less than V1. So this voltage is VE, correct? So only when VE is greater than V1, you have a potential difference. You have a potential difference, and you are having a current to flow, right? So as long as VE is less than V1, current will not flow. So only when VE is greater than V1, the diode is forward biased and the current will flow into the device. So that is what is given here. If a positive voltage VE is applied to the emitter, the PN junction will be reverse bias until VE is less than V1. So the condition for PN junction to conduct is VE should be greater than V1. So if VE exceeds V1 by cut-in voltage V gamma, the diode becomes forward bias. We know that for a diode to become forward bias and start conducting, the input voltage should be more than the cut-in voltage. So VE should be greater than V1 by a cut-in voltage V gamma. So under this condition, holes are injected into the N-type bar. Holes are repelled by the terminal B2 and are attracted by the terminal B1. So this causes the current to flow, and the device is said to be in on state. See here, you have VBB, right? So this base B2 is connected to positive, okay, and B1 is connected to negative. So here you have positive, negative. So because of forward bias, holes will be injected into the N-type region, and here you have positive, so holes will not go to B2, holes will go to B1, contributing to the current. That is what is mentioned here, you see. So when the V is more than V1 by V gamma, holes are injected into the N-type bar. So these holes cannot go to B1 because B1 is positive in polarity. So they will match B2, sorry, and they will be attracted towards B1, which is considered the negative of the battery. So when more holes are going to flow from E to B1, it reduces the resistance, and hence the emitter current is going to be more and more. And this device is said to be now in on state. So when you apply emitter voltage, immediately the device will not conduct. The device will conduct only when the voltage is more than V1. Only in that condition you have emitter current flowing through the device. When a huge amount of current is flow through the device is said to be in